So how does something so large and heavy like an airplane manage to fly? To be able to fly, there must be a way of achieving lift. Lift can be developed in different ways. One of the first ways man managed to fly was by the invention of the hot air balloon. The lift needed to make the balloon fly is created by using hot air. Hot air is less dense than cold air. This reduction in density means that the hot air is light and able to rise through a column of cold air. Instead of using hot air, modern airships use gas that is lighter than air. Although airships are not practical for the transportation of people due to their slow speeds, development in recent years has gone into building airships for the purpose of carrying cargo. One very unusual design in airplanes was the Plymouth AA2004. This plane used rotating drums to produce lift. It was recorded to have flown over Long Island a few times, but the development stopped over concerns that if the engine that rotated the drums stopped, the drums would no longer produce any lift. The Harrier jump jet was developed in the 1960s. This kind of fighter jet used vectored thrust to allow the airplane to take off without the need for a runway. Although the vectored thrust can produce lift for takeoff, hover and landing, the airplane still needs wings to produce lift when flying in cruise. Wings are the best solution for generating lots of lift. The wings on an airplane is really a type of airfoil. An airfoil is designed to interact with a flow of air to provide stability, rotation, thrust, and, as in the case of our talk, lift. It's time to go into detail on how lift is created, but first we need to understand the different types of pressure. Static pressure is created by molecules pushing against a stationary object. If the object were to start to move, there would be a reduction in the molecules pushing against the object. There is another type of pressure called dynamic pressure. This pressure is created when an object starts to travel. Dynamic pressure can be felt on your face and through your hair when you take a trip on a roller coaster, for example. As the roller coaster speeds up, you will feel a force against your face and through your hair. The force you feel is dynamic pressure. Lucky for us, learning to fly doesn't mean we have to take a trip on a roller coaster. Daniel Bernoulli was a Swiss scientist who was born in 1700. Daniel wrote a masterpiece about the relationship between the velocity of a fluid and its pressure when travelling through a venturi. A venturi, by the way, is a tube with a constricted section in the middle. A venturi can be used for measuring the flow rate and pressure. Daniel discovered that when a fluid passes through the constricted part of a venturi, the fluid will accelerate and travel faster. However, the total pressure across the tube remains the same. The static pressure through the constricted area of the tube will drop, so there needs to be an increase in dynamic pressure for the total pressure to remain the same. Although not stated in Bernoulli's principle, it is interesting to note that the temperature of the fluid when entering and travelling through the constricted area of the tube will fall and then start to rise again as the width of the tube starts to expand. There are many different ideas when talking about lift, especially the relationship between Bernoulli's principle and lift. The reason for the controversy is because a wing is not really a complete venturi. If we look at the wing's cross-section, we can see the wing looks similar to half a venturi. I will now give you my opinion on this subject. As the wing travels faster through the air, there will be less impact from the static air molecules. The total pressure around the wing will need to remain the same, so we must increase dynamic pressure. If we make the wing curved on the top, the airstream flowing over the top of the wing will speed up. The airflow over the top of the wing will create a significant reduction in static pressure. The greater static pressure differential between the top and bottom of the wing will create lift. So that is Bernoulli covered. I shall now go on to one of Britain's most famous physicists and mathematicians of the 17th century. As you may remember from your high school days, Sir Isaac Newton made up 3 laws regarding motion. It is Sir Isaac's third law we are interested in with regard to lift. His third law states that when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in the direction on the first body. This law is also commonly referred to as the action-reaction law. Let's investigate how Newton's third law plays a part in the creation of lift. As the pilot changes the wing's angle, the under part of the wing is more exposed to a force created by the relative airflow. The relative airflow will strike the bottom of the wing, which results in the wing being pushed upwards. This pushing up effect has the same effect as lift. Newton's law can even be used to create lift on a flat surface such as a kite. Time for a summary. We have studied that when a fluid travels through a venturi, the fluid will accelerate. At this point in the venturi, there will be a reduction in the static pressure. Lower static pressure on the top of the wing is needed to produce lift. The greater the static pressure differential between the upper and lower parts of the wing, the greater the lift created. We also looked at Newton's third law. We now understand that when the relative airflow, or relative wind as our American friends call it, strikes the bottom of a wing, the wing is pushed upwards.